Hey, this is Cooper, and we're still doing machine learning. Let's get nonlinear. So let's talk about what we've done so far. So last time we talked about the perceptron. We discovered this little model, which was nice and tidy, and then we extrapolated this into the idea of a neural network with these layers of weights where we multiply through these layers to get our output. And we had our hidden layer here, which we had to define the size of, where we had the input and output already designed by the problem that we were tackling with it. We also decided to create this right here, which is the surface of our loss function with respect to our parameters. And what we noticed was that when we initialize our parameters to some point, we'll get some loss right here. So if we initialize our x to this and our y to this, if they're both parameters, then we'll get some loss. And what we discovered using 233 is that if we look at the gradient of this, that is the partial derivative of each of the parameters with respect to loss, then we saw that that was the direction of steepest ascent up this curve. That is the direction that will increase the loss the most if we step in it. What we know, though, and a neat little trick for us, is that if we go in the opposite direction, the exact opposite direction, the negative gradient, that is the direction of steepest descent, which is the direction we want to move. We want to decrease our loss as much as possible. Now, to get this, we needed some tricks, and we came up with this down here, which is our nice way of being able to get the partials of these weights right here, which are not obvious how we might get them, and we can actually use the chain rule, which again we learned in multivariable calc, to calculate each of these. So we can calculate the partial derivative of each of these weights using this simple rule. And we also defined some way for us to actually do these updates instead of just saying this is the direction we move. Now we have an actual rule for it. We have SGD. So stochastic gradient descent works as such. We will subtract from the weights at any given step the learning rate times the partial derivative. That is, we're moving in the direction of the gradient multiplied by some learning rate. So if the learning rate is very small, we'll take very small steps in this direction. If it's very small, that helps us move more and more correctly, and if it's large, it lets us move faster. So we need to balance those two. This, of course, is a hyperparameter, as we heard before, so we will have to choose this before we train the model, and that will determine how it runs. But it's totally arbitrary, not totally arbitrary, but we get to choose it, right? So we saw that when we try out stochastic gradient descent, in general, it will move something like this. So a little bit janky. It'll move in the direction of the gradient, and then it'll find the new gradient, move in that direction, and so on. This is not ideal, but it does converge fairly well. We did see in the last lecture some other method that we could use to do this, and of course there are many. Go check that one out if you want to see what that is. All right. So what are we actually doing when we're doing our neural network? So this is a simple perceptron again, and of course we have our weights. We're multiplying them each. You know, we saw this before, that this node is now equal to this weight times its appropriate input, and we just sum them all up together. What we notice, though, is that this is exactly the same as taking the transpose of the weight times x. This is just a matrix multiplication. So all we're actually doing is a simple matrix multiplication of this matrix. Of course, they're 1D here, so it's not very interesting, but these 1D tensors times these 1D tensors. Again, tensors are the general term for a vector, a matrix. They are a 1D tensor, 2D tensor, respectively. All right. So it's a simple matrix multiplication. So let's look at an actual neural network now. We have our first layer weights, we have our second layer weights. So what are we doing here? If we feed in the x, what we're actually calculating is this function right here. So we're doing the transpose of the first set of weights done on x, and then we're doing the second set of weights transposed on x. If you forget what transpose is when we take a matrix and we flip its rows and columns. That is, for each element, we switch which row it's in with its column and its column with its row. You can think of it as just flipping along the diagonal of a matrix. So we're just doing a simple matrix multiplication on a matrix multiplication. That's all we're actually doing in the neural network we've described. So let's talk about nonlinearities, and in particular, let's talk about this. So if we have some matrix multiplied on x, and we have some matrix multiplied on that new matrix we've gotten, What we can see and what we know from linear algebra, if you remember it, is that these are actually exactly the same as multiplying by a single matrix. And this is a property of matrix multiplication, and what we want to take away from this is that we have two layers. It is the exact same type of computation as having a single layer. In particular, if we have any linear functions, or affine functions in particular, that we are concatenating together like this, we're actually going to end up with a single affine function. And what you can think about is, if we only have a linear function, then what sorts of functions can we represent? And I'll give you an example right now as to why that matters. So let's look at an example. So here is just some data, right? And say we have these points right here. So we have these purple points are one class, or some class, and these yellow points are some other class. And we are tasked with classifying between these and training our model to do so. So how would we actually separate these two classes with a linear function? That is just a line in between them. And we can see, like, let's try it. Maybe put it here. I mean, that's in line with these two. It's about as good as we can get there. And of course, we have one on the opposite side, so this is not correct. We can try it here, and of course, it still does not separate them. And what we actually know from this is that you cannot separate them with a line. This is called, this specific example of having them in the opposite corners is called the XOR problem. So you can see why it would be called that. If we do the XOR operation, it can't actually solve it. And this is actually a sort of historic thing for neural networks and the perceptron. Back in the day, perceptron was invented and stochastic gradient descent and all these wonderful things. But then someone came up with this counterexample, and the perceptron was totally unable to solve it, and it was slightly ridiculed. And for a long time, people were not interested in neural networks because it seemed like it could only do very, very simple, dumb problems, and no one was interested in that at the time. So there is a solution, as you might have guessed from where this is going. What we're going to do is we want to make our neural network into a nonlinear function. So right now it's a linear function. We want to make it nonlinear. So what we're going to do is we're going to add a nonlinear function to its operation. So what that's going to look like is we are going to, instead of having, as we have before, just BAX, so we're not doing matrix multiplication, which is equal to a single matrix multiplication. What we're going to do instead is create some operation sigma here and do it in between the two matrix multiplications. And this sigma right here will be some nonlinear function. And what we'll see is that this cannot be represented by a single linear function. So this is an interesting little property for us. So this is actually true. This sigma can be any nonlinear function. This is an interesting theoretical finding for neural networks, which was that if we have any nonlinear function here, then hypothetically a two-layer network like this, where we only have these two weight matrices, could represent any nonlinear function as long as we have the appropriate nonlinear function in it. So what properties would we like from our nonlinearity right here, this nonlinear function? What would we want? Imagine we are doing our training, we are going through this operation, and then we're doing our backpropagation, our stochastic gradient descent on this new operation that we're doing. And I want to give you a second to try to think on it. It probably won't come to you immediately, but try writing it out and see what sorts of issues you might come into when you're trying to do backpropagation in particular. After you take that second, you can continue now. So what we really want to see from this function is that it is differentiable, and in particular, we want it to have a quick and easy derivative. So every time we do a backpropagation, we're going to have to do a chain rule, not only now just through these two weight matrices, but now through our nonlinearity as well. So if it has a difficult derivative or it isn't differentiable, we can run into problems. If it's hard to compute, it will take a very long time to compute it so many times over and over and over again. And if it is non-differentiable, then we might end up not being able to derive it, and then we can't backpropagate. So I'm going to show you a couple examples of the most popular nonlinearities, or as they're sometimes called, activation functions. This has a meaning in hardware, and we do adopt it here somewhat. but you can just call them nonlinearities if you'd like. But if someone says activation functions, they're also talking about nonlinearities. All right, so the first one we're going to talk about is sigmoid, which is 1 over 1 plus e to the x, where x is the input into our nonlinearity. So this function looks like so. What it does is it caps off the extreme values. The more extreme negative it goes towards 0, and the more extreme positive goes towards 1. But here at the center, it is roughly just x. So we do kind of like that property, and it's all well and good. But the most nice thing about this is that if we look at its derivative, and you can take a second see if you can solve it, its derivative is actually 1 minus like what its value is times what its value is. The nice thing about this is that when we are doing our forward pass through our network, we actually calculate these values. So when we go to calculate the derivative, we've already solved this. We just need to remember it after the forward pass. So this is a really nice little property. It makes computing the derivative very, very fast, which we like. There is a slight adjustment to this one though. So something that people don't particularly like about it is that it goes to 0 for the negative, and you don't actually have your negative values going to something negative, which you might want because you want there to be sort of a relative difference between positive and negative, and you don't really get that when you do sigmoid. You're taking away all of your negative values. So what we actually have is tan h, which is the function that looks almost identical to sigmoid, except it goes down to -1 and up to +1. It does the exact same thing, and in fact, its derivative is also related to its forward pass. So they both have those properties, and they both have the squishing property to keep values from getting too large as we do computation. So they're both nice in a couple different ways. They are not, in practice, actually used that often, though. What has become dominant as a nonlinear function in recent years is this function right here, ReLU, which is rectified linear unit, which is actually just the max function between 0 and its input. So what this looks like is just this. So it's very easy. For any positive value, it stays the same. For any negative value, it stays at 0. So this is a very, very simple function, and in fact, its derivative is also very simple. It is just 0 here and 1 here. So this is very nice, it's very proper, and in fact, the real benefit, you can make a lot of theoretical arguments, but in machine learning we look at the empirical a lot, and this ReLU works much better than both tanh and sigmoid in practice. So that's enough of a reason to do it, but there are some other reasons why ReLU we would imagine would perform better. So first, let's look at sigmoid. So it's generally not used pretty much at all. I'll let you think for a moment why that might be. And again, I'm going to ask that you think about backpropagation, think about actually taking the derivative of this, and think about what might happen when you do that. I'll give you a moment. So the real problem with it, the biggest problem with it, is that when we have very large values, imagine we have an input that is very large going into our sigmoid, we end up with our value down here somewhere as being 0.1 or being 1. What we see is that when we go to backpropagate through the sigmoid now, the value is very, very small. Its derivative is nearly 0. So what we actually see is that the changes get smaller and smaller and smaller as the values get bigger and bigger and bigger, which we don't want to see. We want to see them be roughly proportional, or we want them at least to be sizable enough to be making changes. So as it gets too big, as our values get too big or too small, this collapses and we basically don't have any gradient anymore. We call this the vanishing gradient. So with tanh, you can imagine we actually have a very similar problem. It is a bit better in that it is zero-centered, which we do like to see, and it has this negative proportionality to the positive. Both of these things make it slightly better, but it does still suffer from the same issue. So in general, both of these are not used in common practice. And this one is. You can see a couple of problems with it on your own right here. For example, it just has a 0 derivative for any negative values, which we don't really want. And it also has this discontinuity right there. But in disregarding all of that, this is by far the most used and most beneficial in practice of all of the nonlinearities that are all nonlinearities on this list. But in general, it's the most popular. There are variations of it, like one that is leaky ReLU, which has a slight negative slope instead of just a 0. But in practice, it is not much better. So in reality, most people just use ReLU. And this is one you really actually should remember if you're interested in machine learning at all. I would highly recommend you know what ReLU is. All right, so that wraps it up on nonlinearities. We'll be talking about convolutions next, so get ready for that. See ya.